7.3, Radians and Arc Length. Degrees are the oldest way of representing angle measure, but they're not the most effective. I mean, why are we using 360 as our base anyway? The Babylonians? Radians are better. They rely on something much more fundamental, and to demonstrate, we need arts and crafts. Acquire a piece of string, tape, and scissors. A family member's hoodie is a likely source for the string. Joke, that's a joke. 1. Cut the string so it is less than half the width of this paper. 2. Tie a pencil to one end and tape the other end to the middle of this page. 3. Gently pull the string taut and, using the pencil, trace the circle defined by the length of the string. The center will be where you taped the string. Finally, place your scissors as close to the tape and pencil as possible and carefully cut the string free, like that and like that. Save the length of string you now hold. What is special about it? And there is a glaring, blazing hint. Using your string, physically measure how many lengths does it take to get around the whole circle. Does this make sense? And why? We'll answer this question later in the packet if you haven't been able to answer it yourself already. But do pause the video and try it. Now, on your circle, use a straight edge to draw X and Y axes passing through the center. Starting from the positive X-axis, lay your string along the edge of the circle, moving counterclockwise. Make a point on the circle where the string ends. I'm not going to be able to effectively draw the behavior of the point at the end of the string, but I will highlight what you're going to be doing there. You want to take your string and lay it along until you reach the end of its travel. It'll probably happen right about there, roughly speaking. Again, lay it along and then pause and mark where it lands. If this has all been confusing, or if you just want another round of reinforcement, I highly recommend you watch the linked YouTube video. It's a less than 1 minute explainer that does so with beautifully concise and clear animation. And this leads us to the definition. A radian is the angle measure swept out while traveling one radius length along the circumference of a circle. This is our superior angle measure that I think is so much better than 360 degrees. Now, how many radius lengths did you say it took to get around the whole circle? If you said it was about 6 and maybe a third, you're correct. Because what this really is heading towards is it probably actually took you 6.28 and a few more decimal places to get around the whole circle using radius lengths. And that's because 360 degrees corresponds to 2 pi radians. Now, we frequently have to convert between radians and degrees, so developing a ratio, a fixed ratio for these two, is very valuable. To do so, if we want to find what 1 radian is in degrees, we would need to divide both sides of this equation by 2 pi. So let's do it. the upshot, after we simplify and all the dust settles, is that 180 degrees over pi equals 1 radian. So there's our first conversion factor. 1 radian is 180 degrees over pi. By similar token, 1 degree is going to be pi radians over 180 degrees. Now, let's use these. I want to convert 330 degrees to radian measure. Give a precise answer, no decimal approximations. Oh, I have a slight typo. That should not be there. 1 degree is simply pi over 180 radians. Back to our conversions. Convert 330 degrees to radians. So we'll do 330 degrees, and we know that 1 degree is pi over 180. That wasn't a typo. That should have been there. Let's keep going. We'll have 330 degrees over 180 degrees. Now, let's see what cancels. Our degree units cancel. 330 over 180 have quite a bit of simplifying that can happen. And when it's all said and done, this gives us 11 pi over 6 radians. Next, we want to convert 2 pi over 3 radians to degree measure. We'll do 2 pi over 3, and the unit we will use this time is 180 degrees over pi. We would like to have degrees at the end of this, so that unit needs to be on top. Our pi's cancel out. 3 and 180 also cancels out. So this 2 times 60, this gives us 120 degrees at the end. Now, this next piece is important. Radian measure is unitless. This means that when you give an answer of 2 pi radians for an angle, we simply say and write 2 pi. If you tell me that the angle was 2 pi, I'll know you're speaking in radians. In fact, if you tell me that the angle is 3, I'll presume you're speaking in radians because you use no unit. Let's move on to arc length. Because radians are defined using the original definition of circumference, c equals r times 2 pi, they can be used to calculate the arc length of smaller sectors of a circle as well. If the circumference of a circle is c equals r times 2 pi, what is the length of a half circle? Well, let's take r times 2 pi and cut it in half. That appears to give us r times pi. Interesting. Let's keep going. What is the length of 1/4 of a circle? Okay, easy, same idea. r2 pi, this time we're going to be multiplying it by 1/4. And I'm going to get r times pi over 2. Okay, so r times pi over 2, and then what is 90 degrees in radians? Well, we need to use the pi over 180 conversion factor there. And I'm going to get pi over 2. Wait, Wait, okay, so that means that 90 degrees is pi over 2, and we just said that the arc length of 1/4 of a circle was r times pi over 2. It's r times that angle measure. And yeah, if we're looking at 1/4 of a circle right there, that's 90 degrees for sure. Okay, so this is the definition. For a circle with radius r, the arc length s swept out on a circle by an angle theta in radians is r times theta, r times the angle measure. Okay, what is the arc length when sweeping out 60 degrees on a circle with radius 8? Well, okay, so we know that arc length is the radius times the angle measure, and that gives me 480, wait, degrees? No, we're supposed to be getting a length here. That's not that's an angle measure. Okay, so I have just committed a very common error. I have tried to find arc length by using an angle measure that was not in radians. I've used an angle measure that was in degrees. We have to convert 60 degrees to radians first if we're to use it in the arc length formula. That gives us pi over 3 radians. Now, if we say 8 times pi over 3, that's 8 pi over 3. That is a perfectly acceptable arc length measurement. Circular reasoning. Below is a fresh copy of the unit circle. You should relabel this one in terms of radians rather than degrees. The book has a chart on page 283 giving sine and cosine values of common reference angles. Use them to provide coordinates for each point on the circle. And I'm going to show you how to get started on this one using angles in the first and second quadrant. So we still start out at 0, and we know that the coordinates of this point, because it's a unit circle, are 1, 0. So that means that the sine of 0 degrees and 0 radians is the same, so is the cosine. Cosine of 0, I don't need parentheses there. Sine of 0. Now, at 90 degrees, we can also work with that. We just said that 90 degrees was pi over 2. We already did that conversion. So let's go ahead and say pi over 2. And the point will be 0, 1, which we know by good common sense because it's a unit circle. And so what this tells us is that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. Now, let's get into something that's not 0 or 90 degrees. Let's use 45 degrees. So 45 degrees would be my point right here. And we know, courtesy of our conversion factor, that is pi over 4 radians. Now we also know that this point, if we were to use triangles, would have the coordinates root 2 and 2. So we can say that the cosine of pi over 4 is root 2 over 2, and the sine of pi over 4 is also root 2 over 2. Now, let's next take a look at what would be 135 degrees back in degree world, but which we can label a little more elegantly, or determine a little more elegantly using radians. So our first travel to here was pi over 4. Now, we travel another pi over 4 to get to 90. Well, what's 2 pi over 4? Oh, 2 pi over 4 is just pi over 2. Hey, there you go. And if I travel yet another pi over 4, how many pi's over 4 have I traveled? Well, this was 1 pi over 4. This was 2 pi's over 4. This should be 3 pi over 4. And let's test that. We know it's 135 degrees. Let's test that. Well, and we do our cancellations, and sure enough, yeah, we get 3 pi over 4. Okay, again, properties of triangles and of x and y, we know that because of the reference angles, we're going to have almost root 2 over 2, root 2 over 2. What's the one alteration? Well, the negativity. Because we are in the second quadrant, x values are negative, so we know that that first value, the cosine of 3 pi over 4, must be negative root 2 over 2, and the sine of 3 pi over 4 would be positive root 2 over 2. You can continue in this same vein. You'll definitely need to write smaller than I am, and you may also want to generate other copies of this unit circle to fill out and refer to.